Tonight we're going to talk about a number. Not a big number in the way that $1 million is a big number, or even $1 billion. A number so large that the word large stops meaning anything useful. A number that has been revised upward dramatically, not once, not twice, but multiple times in the last 30 years. And each revision has come with the same quiet, uncomfortable admission from the scientific community. We were wrong. We undercounted. The universe is larger, fuller, stranger than we thought. And the most recent revision, the one that is still being worked out right now using the most powerful telescope ever built, suggests that everything we thought we knew about how the universe began, how galaxies formed, and what the early cosmos looked like may need to be rewritten from the ground up. Let's start with Carl Sagan. Most people who grew up watching science programming in the 20th century heard one phrase more than any other when the subject turned to the scale of the cosmos: billions and billions. It became shorthand for incomprehensible scale. Billions of stars in the Milky Way. Billions of galaxies in the universe. The phrase attached permanently to Sagan's name, even though he never actually said those exact words in his television series Cosmos. It did not matter. The phrase captured something true about how he talked about the universe. The repetition of the word billions was the point. It was a gesture toward a scale the human mind cannot actually hold. But the specific number of galaxies that Sagan and his contemporaries were working with was approximately 100 billion. 100 billion galaxies in the observable universe, each one containing hundreds of billions of stars. Each one a city of suns so numerous that if you spent 1 second on each star in a single average galaxy, it would take you 3,000 years to finish. Multiply that by 100 billion, and you arrive at a number that has stopped functioning as a number and become something more like a philosophical position. That was the answer. 100 billion galaxies. It was written into textbooks, cited in documentaries, repeated in classrooms, absorbed by generations of students as settled fact. It was the foundation on which everything else about the scale of the universe rested. It was wrong, not slightly wrong, not off by a comfortable rounding error, wrong by a factor that is itself difficult to state out loud without it sounding like an exaggeration. And the story of how we found out, and what we have found out since, is one of the most important stories in the history of science that almost nobody outside the field has fully registered. Here is how the number 100 billion was arrived at in the first place, because understanding the method is essential to understanding why it was so confidently stated and why it turned out to be so far off. Counting every galaxy in the observable universe directly is not possible. The observable universe is a sphere roughly 92 billion light-years across. Even at the speed of light, crossing it would take 92 billion years. The number of objects inside it is beyond any direct inventory any civilization could ever conduct. What astronomers do instead is something more practical and more ingenious. They point a telescope at a very small, carefully chosen patch of sky. They count every galaxy visible in that patch with the best instruments available, and then they multiply that count across the entire sky to produce an estimate. Think of it like this. Imagine you want to know how many blades of grass are growing in a large field, but you cannot possibly count every one. So you mark out a small square, count the blades inside it carefully, and then use that density to estimate the whole field. The accuracy of your answer depends entirely on two things: how carefully you counted within the square, and how representative that square was of the whole field. If you happen to pick a square that was unusually sparse, your estimate will be too low. If you happen to pick a square that was unusually dense, it will be too high. For most of the 20th century, the instruments astronomers had were good enough to count the bright galaxies in their sample patches, but not nearly good enough to detect the faint ones. And the faint ones, it turned out, were not a minor footnote. They were the majority. In the early 1990s, the Hubble Space Telescope changed the game. Hubble's deep-field images were among the most consequential photographs ever taken. The technique was straightforward in principle and almost absurdly ambitious in execution. Astronomers pointed Hubble at a tiny patch of sky, a region equivalent to the size of a pinhead held at arm's length, a patch that in ground-based images appeared to contain essentially nothing, just darkness between the nearby stars. They kept the shutter open for days, not hours, days. They allowed light to accumulate on the detector over an exposure so long that even the faintest signals had time to register. What appeared in that image stopped people cold. The tiny dark patch was not dark at all. It was full. Thousands of galaxies, each one a complete island of hundreds of billions of stars packed into a region of sky that had looked completely empty. Different shapes, different colors, different distances, some of them so far away that their light had been traveling for billions of years before entering Hubble's mirror. The darkness between the stars was not empty. It was full of galaxies we had simply lacked the sensitivity to detect. From those deep field images, and from similar surveys that followed, astronomers revised their estimate upward from the earlier rougher counts and settled on a figure of somewhere between 100 and 200 billion galaxies in the observable universe. That number held for about 2 decades. It became the new standard answer. It was Sagan's billions and billions made precise, and it was still wrong. In 2016, a team of astronomers led by Christopher Consolis at the University of Nottingham did something that had not been done before. They took Hubble's deep field data and converted it into a 3-dimensional map of the universe across different epochs of cosmic time. They were not just counting galaxies as seen from Earth. They were reconstructing how many galaxies existed at each stage of the universe's history, on and then using mathematical models to account for all the galaxies that even Hubble could not see. The ones too faint, too small, too distant, too obscured. The ones that would only become visible to instruments more powerful than anything that existed at the time. The result was not a modest revision. Their calculations suggested the observable universe contains not 100 billion galaxies, not 200 billion, but at least 2 trillion, 2,000 billion, a number 20 times larger than the figure that had been standard for 2 decades. And the galaxies Hubble could actually photograph, the ones that formed the basis of the previous estimate, were by this calculation only about 10% of the total. 90% of the galaxies in the observable universe were invisible to us. Not because they were beyond our horizon, not because they were outside the region from which light can reach us. They were right here, within the observable universe, simply too faint and too small for any telescope yet built to detect. Think about what that means. The observable universe is, by definition, the part of the universe we can see. The light from those galaxies has reached us. There is no physical barrier between us and them. They are not hidden behind anything. We just did not have eyes sensitive enough to find them. For 20 years, the standard answer to one of the most fundamental questions in all of astronomy was off by a factor of 20. Not because astronomers were careless, because the instruments they had could only show them a fraction of what was actually there. And the revision was not finished. Because in December 2021, after decades of development, at a cost of $10 billion and a launch that held the attention of the entire scientific community, the James Webb Space Telescope opened its eyes. What it saw was not what anyone expected. Webb was built to see further back in time than any telescope in history. Because it operates in infrared light rather than visible light, it can pierce through the dust and gas that obscure the earliest galaxies and detect objects so distant that their light has been traveling for more than 13 billion years. The early universe, the universe as it existed in the first few 100 million years after the Big Bang, was finally within reach. Astronomers had detailed theoretical models of what they expected to find. Models built over decades, refined through thousands of papers, tested against everything Hubble had been able to show them. They expected small, faint, young galaxies, infant structures barely beginning to coalesce from the gas and dark matter of the early cosmos. A rough draft of a universe that had not yet had time to build anything impressive. What Webb found instead was galaxies that had no right to exist. Massive, structured, developed galaxies, sitting in Webb's data from a time when the universe was only 500 to 700 million years old. Not small, not simple, not rough drafts. Galaxies containing as many stars as the Milky Way contains today, in a universe that had barely had time to turn the lights on. One of the objects identified in the initial data appeared to contain a mass of stars equivalent to roughly 100 billion suns. The Milky Way, which has had 13 billion years to build itself, contains roughly 60 billion solar masses of stars. This galaxy, observed at a time when the universe was only about 3% of its current age, appeared to have already matched or exceeded that. The timelines did not work. The galaxies had not had enough time to exist. Ivo Lebey, an astrophysicist at Swinburne University of Technology and one of the lead researchers on the initial discovery, described the revelation simply. He said that massive galaxy formation had apparently begun extremely early in the history of the universe, in a way that upended what many scientists had thought was settled science. Joel Leja, an astronomer at Penn State who co-authored the study, was more direct. He said the findings called into question our understanding of how the earliest galaxies formed. Now it is important to be precise about where the science currently stands, because not every headline that emerged from those early Webb observations survived closer scrutiny. Some of the apparently monstrous early galaxies turned out to owe their extraordinary brightness not entirely to stars, but partly to supermassive black holes blazing at their centers, their accretion disks outshining everything around them. When those were accounted for, some of the galaxies became less impossibly massive. The most extreme cases were walked back, but not all of them. Even after the corrections, the data still shows roughly twice as many massive galaxies in the early universe as the standard model of cosmic evolution predicts. The problem has not been solved. It has been made less sensational while remaining completely unresolved. And Webb has continued operating, continued gathering data, and continued finding things that do not fit the script. In 2025, a team from the University of Missouri identified 300 unusually bright objects in Webb's data that may be among the earliest galaxies ever formed. Objects whose brightness cannot be fully explained by current models of stellar formation. A team from Texas A&M found a collision of at least 5 galaxies taking place just 800 million years after the Big Bang. A level of complex galactic interaction that models predicted should not occur until well over 1 billion years into the universe's history. And Webb's observations of the most distant galaxy ever confirmed, observed as it existed less than 300 million years after the Big Bang, revealed unexpected oxygen in its spectrum, an element that requires generations of stars to produce and has no business existing in a galaxy that young. The universe of the early Webb data is consistently, repeatedly, in finding after finding, more developed, more complex, more structured than our models said it should be. And the current best estimate for the total number of galaxies in the observable universe, incorporating everything both Hubble and Webb have contributed, now sits somewhere between 6 and 20 trillion. Not 2 trillion, between 6 and 20 trillion. The lower bound of that range is 60 times larger than the number that was standard for 2 decades. The upper bound is 200 times larger than what Carl Sagan's billions and billions was gesturing toward. There is a pattern in this history that is worth stating plainly, because it is not accidental and it is not finished. Every time astronomers have built a better instrument and pointed it at the sky, they have found more than the previous instrument could show. Not occasionally, every single time. The history of this particular question, how many galaxies exist, is a history of revision always moving in the same direction. Upward. The universe has never turned out to be simpler or smaller or less populated than we thought when we looked more carefully. It has always been larger, always fuller, always stranger. The direction of the error has been perfectly consistent across a century of improving observations. This is not a coincidence. It is telling us something about the relationship between our instruments and reality. At any given moment, the instruments we have built can only show us a fraction of what is actually there. And because we are human, and because we have a strong tendency toward the assumption of typicality, we treat that fraction as representative. We count what we can see, and we call it the answer. And then we build a better telescope, and we discover that what we could see was not the whole picture. It was never the whole picture. The number you learned in school was wrong. Not because anyone lied to you, because the instruments available when that number was established could not see what was actually there. The number that replaced it was also wrong for the same reason. The current number, 6 to 20 trillion, is the best estimate available with the best instruments currently operating. And when the next generation of telescopes comes online, when the extremely large telescope currently under construction in the Chilean desert begins its observations, when instruments we have not yet designed become possible, that number will almost certainly change again. The direction of the change is not hard to predict. Here is the last thing I want to leave you with tonight. We are living at a specific moment in the history of this question. We are the generation that got to watch the number double, and then multiply by 10, and then multiply by 10 again. We are the generation that watched the most powerful telescope ever built point at the early universe and find things that broke the models. We are not watching this from a textbook. We are watching it in real time, paper by paper, discovery by discovery. I'm each one quietly dismantling the previous answer and replacing it with something larger and stranger. The universe is not getting bigger. It has always been this big. We are just getting better at seeing it. And every time we see more of it, we discover that what we were so confident about last decade was a shadow of the reality, a sample that was not representative, a count that missed 90% of what it was counting. There are between 6 and 20 trillion galaxies in the observable universe right now. That is the current best answer. It is probably still too small. And somewhere in all of that, in all those trillions of galaxies, in the data still arriving from Webb, in the anomalous brightness of objects that appeared too early and grew too fast, in the findings that do not fit and the models that are being quietly rewritten, the universe is doing what it has always done when we look closely enough. It is being more than we thought. Good night.